let's talk about what the FAA wants you to know about assembly and rigging. And I guess that means putting them together right and making sure they fly right. Let's lead off by talking about some terms they want you to know. And one of those terms has to do with airfoils, and it's the chord of a wing. Now, the chord is from the front of the wing to the back of the wing. That's not the way they put it on the test. They say the chord of the wing is measured from the leading edge to the trailing edge. And a lot of times you have the average chord, so that you have the average length from the leading edge to the trailing edge of the wing. Now, another thing we want to talk about is the span of a wing. And the span is from wingtip to wingtip. It's the distance from the wingtip to the wingtip, and that's the span of the wing. Now, another thing they're going to ask you about is the aspect ratio. And the aspect ratio is the ratio of the span to the chord. And that's the wingtip to wingtip versus the forward-aft length of the wing, or the chord of the wing. And it tells you whether or not you have a high aspect ratio wing, which is a long, skinny wing, or a low aspect ratio wing, which is a short, stubby wing. Now, the two things that you need, though, then, to take into consideration when you're talking about the aspect ratio or the span and the chord. And the way they put that on the FAA written exam is the physical factors involved in the aspect ratio of an airplane's wing are the span and the chord. Now, that's FAA talk. Let's do some more FAA talk, and let's talk about angle of attack. They're going to say to you that the angle of attack is the acute angle. That means a small angle. In other words, here's the small angle. Going all the way around the other way would be the big angle, so the small angle is the acute angle. And it's the angle between the chord line of the wing, and in this particular case, that's a line drawn from the trailing edge of the wing to the leading edge of the wing. That'd be the chord line of the wing to the relative wind. Now, if an airplane is flying this direction, the relative wind is coming from the opposite direction. And so basically the relative wind is opposite the direction the airplane is flying. So here we have the relative wind like so, and this is the chord line of the wing. The angle between those two is called the angle of attack. It's the angle of attack, the acute angle formed by the chord line of the wing and the relative wind. Now, they want you to know, as you increase the angle of attack, the center of pressure moves. Now, center of pressure you can think of as the average lift on the wing, the center of lift on the wing. And as you increase the angle of attack, the center of pressure moves from a rear position to a forward position. It moves forward. Now, the way they put that on the test, as the angle of attack of an airfoil increases, the center of pressure will move towards the leading edge. Now, that's a non-symmetrical wing that happens to. Most wings are non-symmetrical, so you can leave that out. But as you increase the angle of attack, the center of pressure, which you can think of as being the center of lift, moves forward. Now, another concept we need to talk about is angle of incidence. And the angle of incidence has to do with how the wing is mounted on the aircraft. And it's the angle between the chord line of the wing, that's the line that we talked about earlier from the leading edge to the trailing edge, or the trailing edge to the leading edge, that's the chord line of the wing, and the longitudinal axis of the airplane. Now, the longitudinal axis of the airplane is essentially a line drawn from the rear of the airplane to the front of the airplane that passes through the center of gravity, and the airplane rolls about that longitudinal axis. The angle of incidence tells you how the wing is bolted onto the aircraft, and it's the angle between the chord line of the wing and that longitudinal axis. But they don't put it exactly like that on the test. They say the angle of incidence is the acute angle, that means the small angle, formed by a line parallel to the wing chord, because you might need to move it up or down to get it near the longitudinal axis, and a line parallel to the longitudinal axis of the aircraft. That's essentially the same thing I said earlier, but that's just FAA talk. Now, the angle of incidence of an airplane does not change in flight unless you crash the airplane. Then you do change the angle of incidence of the aircraft. Now let's talk about high lift devices, including flaps and slats. Now, these allow you to change the shape of the wing without crashing the airplane first. Now, why do you want to change the shape of the wing? Well, when you're in cruise, you want very little curvature to the wing, but when you're in slow flight, you'd like to have a lot of curvature to the wing for when you're landing and taking off. So you can change the shape of the wing, for instance, with flaps. Now, flaps are at the trailing edge of the wing, and here's several kinds of flaps. Split flaps just simply split away from the wing at the bottom and change the curvature of the wing and increase the lift. Now, anytime you increase the lift on a wing, you also increase the drag, because lift and drag just go together. You can't get one, you can't get lift without drag. Now, another kind of flaps is slotted flaps. As the flap goes down, it creates a slot, and that delays the stall. And then here is a Fowler flap. Now, Fowler flap does something very interesting. It increases the area of the wing, because when a Fowler flap goes down, it also goes back and increases the area of the wing, and that is a Fowler flap. Let's take a look at a Fowler flap in real life. Here you have the flap going not only down but back, also increasing the wing area, and that is a Fowler flap. Now, a Fowler flap increases the wing area as well as changing the wing camber, or the shape of the wing, and that increases lift. And of course, once again, anytime you increase lift, you also increase drag. Now, when lift of an airfoil increases, drag automatically increases. And the FAA wants you to know that. You just cannot get lift without at the same time having a lot of drag. Now, you might ask, we talked about slats. What is a slat? Well, a slat is a movable airfoil on a big airplane like this one here, and it's a movable airfoil at the front of the wing, like so. So there you see a slat, and it's attached to the leading edge of what they call high-performance wings, and the purpose of the slat is to reduce the stalling speed. So it moves forward, and it normally leaves a little space for air to get through, and it changes the shape of the front of the wing, and that's why it's called a slat and not a flap. Now let's talk about stalls. A stall occurs when you increase the angle of attack of an aircraft beyond the critical angle of attack. You would like for an airplane to stall first in the inboard portion of the wings and to stall later out at the wing tips. That way you keep aileron control all the way through the stall. So the purpose of stall strips installed on a wing like so, the purpose of these stall strips is to stall the inboard portion of the wing first. So you have these stall strips to do that, and that way you have aileron control all the way throughout the stall. Now they ask you some questions on buffeting, and buffeting occurs, by the way, sometimes when you're in a stall, and what it is a banging on the aircraft. And they want you to know it's in what's called the intermittent application of forces to a part of the airplane caused by unsteady flow from turbulence. So when you're stalling an airplane, you're actually creating turbulence, and then you have buffeting on the aircraft, and it's the intermittent application of forces on the aircraft. Now let's talk about flight control surfaces on an aircraft. Let's assume you're in the aircraft and you're moving the stick of the aircraft. They're going to ask you a question. If the control stick is moved rearward and to the left, they think it would be a good idea for you as a mechanic to know what happens to the aileron and the elevator. First of all, if you move the stick to the left or a control wheel to the left and rearward, what you want to do is make the airplane turn to the left. So what's going to happen to the right aileron? The right aileron will go down. And if you move the wheel back, that means you're trying to make the airplane climb, and that means the elevator will go up. So if you move the wheel or stick rearward and to the left, the right aileron is going to go down and the elevator will go up. Now, you might guess, will they ask you anything else about this? Yes, they're going to ask you what happens if you move the wheel forward and to the right. So here we are moving the wheel forward and to the right. When we do that now, we're trying to turn the aircraft to the right, so this left aileron will go down. We're pushing forward on the wheel. We want to go nose down, so the elevator will go down. So if you move the wheel forward and to the right, the left aileron will go down and the elevator will go down. The FAA figures that's a good idea for you to know that, so when you hook up these controls, you do them right. All right, now sometimes you have differential controls on ailerons. Let's you and I take a look at differential controls on ailerons. Here's the up travel. It's great deal of travel and less travel on the down part of the aileron. That's what they call differential control on an aileron system, and it means the up travel is more than the down travel. And what that does is that adverse yaw is eliminated or reduced by having it done that way. Not eliminated, but it is reduced. Now they ask you a question on a test about the indicating systems for the primary control surfaces of an airplane. In order to be able to answer this question, you have to understand what are the primary control surfaces of the airplane, and they are, of course, aileron, elevator, and rudder. Those are the primary control surfaces of the airplane. So if you have a flap indicating system, indicates the flap position, does that have anything to do with the primary control surfaces? No, it would not. How about a speed brake indicating system? No, it would not. How about elevator trim indicating system? Does that have anything to do with the primary control surfaces of the aircraft? And the answer is yes. Elevator trim indicating tells you the proper trim position for instance, takeoff in this particular case, or maybe landing. And it has to do with the primary control surfaces because the elevator is one of those primary control surfaces of the airplane. Now let's talk about a tool you might use to measure the degrees of aileron travel, and that tool is the Universal Propeller protractor. And you use this level to measure degrees of aileron travel and flap travel, and it should be zeroed with the aileron in the neutral position. So they want you to know, zero this with the aileron in the neutral position. That's called the universal propeller protractor. By the way, it can also be used, as I said earlier, to measure degrees of flap travel, and that's the universal propeller protractor. Now let's assume as a mechanic you've done some work on the rudder of an aircraft. Maybe you've repaired it or recovered it. What should you do next? And the answer is you should balance the control surface according to the manufacturer's specifications, because if it's not properly rebalanced, you could have control system flutter. Now, how do you go about rebalancing it? Well, you can put it on a control surface on a balance stand. This would be a balance stand, and mount it by its hinge points, and then see what happens. And if the trailing edge of the control surface comes down, then it's underbalanced. And if the trailing edge goes up, it's overbalanced. And by the way, if you have any trouble remembering this, this is the underside, this is the overside. So if the trailing edge goes down, it's underbalanced. Trailing edge goes up, it's overbalanced. And that way you can determine whether it's properly balanced. Of course, what you want it to do is not have the trailing edge move at all. Now let's assume that your operation has gone big time. Now you're international. You're importing aircraft, you're reassembling them and selling them. Well, when you reassemble these aircraft, you'd like to know some pretty important stuff. Things like, well, how much flight control surface deflection should there be, say in the ailerons or the other primary flight controls? Well, you might go to the manufacturer's maintenance manual, but to get the most complete information, you'd go right here to the type certificate data sheet. Now let's talk about trim tabs, and two types of trim tabs are servo tabs and spring tabs. Now both of these help the pilot or assist the pilot in moving the control surfaces. Now the way a servo tab works, if you want to move for instance, the elevator up, it goes down and helps provide the force to move the elevator up. A spring tab is very similar. It would do the same thing, but a spring tab has a spring in it so that the very little movement by the pilot doesn't wind up having the tab helping you. Then when the spring gets a little pressure on it, then the tab comes and helps you. They're very similar devices, but they both assist the pilot in moving control surfaces, and that's what you need to know for the written exam. Now they want you to know that when you're inside the cockpit and you have flight control trim systems, the control inside the cockpit, they must be designed and installed so the pilot can determine the relative position of the trim tab from the cockpit. So that's an important thing, and it's got to be accurate, as you might know. So if you install a trim control inside the cockpit, the pilot must be able to see the trim position from inside the cockpit. Now let's assume as a mechanic you're making an operational check of the trim control system, and you move the cockpit control towards the nose down position. They're going to ask you on the test, what's going on back here at the tail of the airplane? Well, you want the nose to go down. That means the tail is going to go up, the elevator is going down. That means the trim tab will go up. So here's the question and the way it will read on the FAA written exam. Movement of the cockpit control towards the nose down position during an operational check of the elevator trim tab system will cause the trailing edge of the trim tab to move upward regardless of the elevator position. And that's what you need to know for the test. Now let's talk about improper rigging of the elevator trim tab system and what would it affect. And the answer is if you improperly rig the elevator trim tab system, it will affect the balance of the airplane about its lateral axis. So if you had the trim tab messed up, that's going to affect the nose up, nose down attitude of the airplane, and it's going to affect it about the lateral axis. Now the lateral axis is a line drawn from wingtip to wingtip that passes through the center of gravity. So we have two of the axes done already. We have the longitudinal axis, which goes from the tail of the airplane to the nose of the airplane, passes through the center of gravity, and the airplane rolls about the longitudinal axis. We have the lateral axis, which goes from wingtip to wingtip, passes through the center of gravity, and the airplane pitches about the lateral axis. And we have the last one we haven't covered, the vertical axis that goes from the floor of the airplane to the ceiling of the airplane, and the airplane yaws about the vertical axis. So the lateral axis is what the airplane pitches about, and that's what improper rigging of the elevator trim tab system would affect the balance of the airplane about its lateral axis. Now, if they talked about along the longitudinal axis, they'd be talking about along this line, but it's about the lateral axis. Now let's talk about wing twist and washing in and out of wings, and we're talking about the angle of incidence of the wing all the way from the root to the wing tip. And washing out of a wing is done by rigging it with a lower angle of incidence to decrease lift. So if you change the angle of incidence of this wing so that you lower the angle of incidence to decrease lift, that's called washing out of the wing. Well, what would be washing in of the wing? And this has nothing to do with cleaning the wing at all. Washing in of the wing is done by rigging it with a greater incidence, angle of incidence, to increase the lift, and that's called washing in. It's used to wash in is increased lift. So if you have any trouble remembering it, wash in increases lift. Wash in increases lift. You got it. I know you had it right there. All right, now let's assume you wash in the left wing of a monoplane for purposes of rigging corrections. Will that increase drag or decrease drag? Well, it'll increase lift and it'll increase drag. And so washing in increases lift and increases both drag and lift and increases the angle of attack. Now, what happens if a pilot reports an airplane flies left wing heavy? It's left wing heavy right here. What do you do to correct that? And the answer is you wash in the left wing. That would increase the incidence of the left wing, or wash out the right wing, or do both if you had a left wing heavy situation. Now, if the right wing of a monoplane is improperly rigged to a greater angle of incidence than the manufacturer's designated specifications, it will cause the airplane to be off balance both laterally and directionally. Now, when we're talking about too much angle of attack in the right wing, the airplane is off balance and it wants to roll. Now, rolling an airplane is expressed as being off balance laterally. And if the airplane wants to turn, it's off balance directionally. So if you have the right wing of a monoplane improperly rigged to a greater angle of incidence than designated in the manufacturer specifications, it will cause the airplane to be off balance both laterally and directionally. Proper wing twist in a sheet metal constructed wing can be checked by utilizing a bubble level and special fixtures described by the manufacturer. And it's a little bit more difficult if you have a sheet metal wing, particularly a low wing like a Cherokee, but you use a bubble level and special fixtures described by the manufacturer. Now let's talk about symmetry alignment of an aircraft. First of all, the aircraft service or maintenance manual would contain the precise information to perform a symmetry alignment check for a particular aircraft. Now, what are we talking about when we're talking about symmetry alignment? We're talking about, are the wings on straight? And is the vertical tail in the proper position? And if the vertical tail of a single-engine, propeller-driven airplane is rigged properly, it will generally be, according to the FAA, parallel to the vertical axis. In other words, it'll be right straight up. But it will not be parallel to the longitudinal axis because you need to have a little bit of an angle there so you can correct for the natural left turning tendency of the aircraft. So if a vertical fin of a single-engine, propeller-driven airplane is rigged properly, it will generally be parallel to the vertical axis, but not to the longitudinal axis of the airplane. Now let's talk about aircraft rigging and rigging checks. Now, an aircraft should be rigged to fly in a hands-off condition in cruise. So you want the airplane to be able to fly hands-off at cruising speed. Now, rigging and alignment checks should be undertaken in the open, and that would be by far the best thing to do. However, if this cannot be avoided, the aircraft should be positioned with the nose into the wind, so the wind is minimized as a factor in the rigging and alignment of the aircraft. Now, if the travel of an airplane's controls is correct, but the control cables are rigged exceptionally tight, the airplane will be heavy on the controls. So if you find the airplane is heavy on the controls, it might mean that they are rigged exceptionally tight, and that causes the airplanes to be heavy on the controls. Let's talk about stability. And to lead off, let's talk about lateral stability. And lateral stability is stability about the axis which runs parallel to the line of flight. Which one that is that? That's the longitudinal axis. The longitudinal axis runs parallel to the line of flight. Lateral stability does not refer to the lateral axis. Lateral stability refers to roll about the longitudinal axis. Now, it is very, very confusing, but that's why they ask you questions about it on the FAA written exam. So lateral stability is stability about the axis which runs parallel to the line of flight, and it's referred to as lateral stability. Now, lateral dihedral And let's take a look at lateral dihedral. Contributes most of the stability about an airplane about its longitudinal axis. Now here's dihedral, and it's the bending up of the wings, and it has to do with stability about the longitudinal axis of the aircraft. That's that same axis we talked about earlier. Now on the written exam, the FAA makes really a sincere effort to confuse you about these axes of the airplane. For instance, they ask you, what is the movement of an airplane along its lateral axis? Well, a movement of the airplane along its lateral axis is the same thing as movement about the longitudinal axis. It's roll, and it's controlled with the ailerons. Movement about an axis means you roll or you rotate about that axis. Movement along means you take the whole axis and move it like so. And so movement of an airplane along its lateral axis is called roll, and it's the same as movement about the longitudinal axis, and it's controlled by ailerons. Now let's you and I take a look at that dihedral angle again. They're going to ask you on the test, how do you measure that dihedral angle of a wing? And one way to do it is place a straight edge and level protractor on the front spar of the wing. So you place a straight edge and a level protractor on the front spar, and you can measure the dihedral angle of the wing. Now, another way is use a dihedral board and bubble level along the front spar of each wing. So a dihedral board and bubble level along the front spar of each wing. So those are two ways to measure the dihedral angle. Now this time let's you and I talk about longitudinal stability. Longitudinal stability is stability about the lateral axis of the airplane, and it controls the tendency of an aircraft to pitch up and down. Now one way you do that is the way you put the center of gravity in the airplane, or design the center of gravity in the airplane, in regard to the center of pressure or the center of lift. And what you normally do is have the center of gravity located in front of the center of pressure, and that way there's an aerodynamic down force on the tail. You can see there would have to be a down force on the tail. If you pick this airplane up by a string where the center of pressure is, you notice the airplane, due to the fact that the center of gravity is ahead of that string, the airplane would have a tendency to pitch down. And to keep it from pitching down, you do have that down force on the tail, and that down force on the tail helps make the airplane stable as far as pitch and speed are concerned. Let's take a look at it. First of all, let's assume you have the airplane flying along, and for some reason it gets hit by a gust of wind, or for any other reason the airplane starts going too fast. That means there will be more air over the tail and more aerodynamic downforce on the tail. The nose will come up, the tail goes down, the nose will come up, and the airplane will climb, lose speed, and return to its original speed. You see that aerodynamic downforce on the tail helps make the airplane stable as far as pitch and speed are concerned. If for any reason the airplane starts to get too slow, now there's less downforce on the tail will come up, the nose will go down, the airplane will dive, pick up speed, and return to its original speed. So the fact that the center of gravity is in front of the center of pressure helps make the airplane stable as far as pitch and speed are concerned. That's called stability about the lateral axis, and it's called longitudinal stability because you're moving the whole longitudinal axis of the airplane. Now the way they put this on the test is an airplane's center of lift is usually located aft of the center of gravity so that the aircraft will have a nose heavy tendency, and they want you to know that. Now, the elevators of a conventional airplane then are used to provide rotation about the lateral axis. The lateral axis is the line drawn from the wingtip to the wingtip, and it's the elevators that provide rotation about the lateral axis, and they want you to know that. Now, an airplane which has good longitudinal stability would have a minimum tendency to pitch. That's what this longitudinal stability is all about, is to keep the airplane from pitching when you don't want it to pitch. Now, an airplane that has a tendency to gradually increase its pitching moment after it's been set to motion is said to have poor longitudinal stability. In other words, if you put the nose up 10 degrees, the nose just keeps on going up, the airplane would have poor longitudinal stability, and they want you to know that on the FAA written exam. Now let's talk about directional stability. They're going to say, all right, what is the purpose of the vertical fin on an aircraft? Well, the purpose of this vertical fin, other than advertising our name of our courses, is to provide directional stability. The purpose of this vertical fin is to provide directional stability. Now, an airplane is controlled directionally about its vertical axis by the rudder. So the rudder controls the airplane about the vertical axis. That's the line from the ceiling to the tail. Now let's talk about weight and balance. And one of the questions they ask you on the test is, what is the buttock line or butt line of an airplane? Now let's try and keep this clean. I'm sorry, that's FAA talk, but the buttock line or the butt line is equivalent to the fuselage station of an aircraft. A fuselage station is how far you are fore or aft from the datum line. Well, the buttock line or butt line of the aircraft is how far you are left or right from the center of the aircraft. It's the width measured left or right and parallel to the vertical center line of the aircraft. So you would say that your fuselage station 108 means you're 108 aft of the datum line. If you said I'm at buttock line or butt line 108, it means you're 108 inches to the left or to the right of the center line of the airplane. Now let's go back to that concept of fuselage station and ask you, what does it mean if you're at fuselage station number 137? Well, what it means is you're located 137 inches aft of the datum line. Now on the test they don't call it the datum line. It's 137 inches aft of the zero or fixed reference line, and that's fuselage station number 137, really 137 inches aft of the datum line. Now let's assume as a mechanic you install radios or avionics in an aircraft and the associated antenna systems associated with those avionics, and let's assume you install them forward of the CG limit. Now the question is this going to affect the empty weight and the useful load of the aircraft? And the answer is yes. Anytime you install some new equipment in an aircraft, including avionics and antennas, it does affect the empty weight and useful load of the aircraft, and you would have to recompute the weight and balance of the aircraft. Now let's assume you want to jack up an airplane to weigh the aircraft for weight and balance purposes, and you're going to do it with a magnificent DC-3. The question is, should you do it indoors or outdoors? And they want you to generally jack up aircraft for weighing indoors. They don't want the wind to affect the weighing of the aircraft. And also they want you to know, before you jack an aircraft, you need to reinstall any critical stress panels or plates, because if you have plates off the aircraft that are load-bearing stress panels and you jack up the aircraft, you could put a stress on other parts of the aircraft that it's not designed for. Now let's talk about flight control system hardware. We'll start off by talking about cables. The smallest cable you need to know that can be used on aircraft primary control systems is 1/8 of an inch, and you need to know that for the test. The smallest cable that can be used is 1/8 of an inch. Now let's take a look at FAA figure number 8, and the FAA is going to ask you a question about this. They're going to say, all right, super mechanic, take a look at figure 8, and you've got 1, 2, 3, and these are cross sections of cables. And the question is, which cable is used in primary control systems and in other places where operation over pulleys is frequent? And the answer is not 1, not 2, but the answer is 3, and this is what is known as 7x19 cable. And it's made up of 7 strands of 19 wires each. And these are very, very flexible cable, and they're used in primary control systems and other places where operation over pulleys is frequent. And the correct answer to this question is number 3. Now, I suppose that you probably think that control cables are pretty important in an aircraft. Well, so do I. And if you're inspecting control cables, wouldn't it be nice to know where you could expect to find problems? You know, little things like broken wires and things like that. So where do you think you're likely to have problems like that? Well, breakage in control cables is predictable, and it occurs most often in places where the cables pass over pulleys like this or through fair leads. In other words, where it changes direction or might make contact with the bulkhead. Now, is it possible control cables could have broken wires where they're swaged to terminal hardware, such as turnbuckles and ball terminals? And the answer is yes, it's possible. They could have wires break at those points, but on a properly rigged cable, you're much more likely to find broken wires at points where the cable changes direction and makes contact with other parts where it passes through pulleys and through fair leads. All right, now the next thing we want to talk about is in a cable-operated control system of an all-metal aircraft, and it does not incorporate a temperature compensating device, and it's been rigged to the correct tension in a heated hangar. Now, if the aircraft is operated in very cold weather, they're going to ask you what will happen to cable tension in cold weather. Well, in very cold weather, cable tension will decrease when the cables become cold, And the reason for that is the aircraft actually shrinks more than the cables do, so cable tension will decrease when the aircraft structure and cables become cold. It's both of the two combined that become cold. Now, if control cables are adjusted properly and the control surfaces still tend to vibrate, they're going to ask you, what is the probable cause? And the answer is probably worn attachment fittings for the control surface. For instance, the elevator tends to vibrate and the control cables are adjusted properly. You better look to see how the elevator is attached to the aircraft itself, because you might have worn attachment fittings. Now let's assume that you've just inspected an aircraft and one of the things that you have decided is that you need to replace the control cables. Well, when you do that, one of the things you'll also need to do is reattach a terminal to a cable. Now, how are you going to do that? Well, these days the way you do it is press it on, or what they call swaging it on. This is called a swaged terminal. Now, when you put this thing together, you want to make sure it lasts. Well, corrosion treatment, it's a good idea. It's not required, but that's one of the things you can do. But the real thing you're concerned about is it strong enough? Well, one of the things you can do is what is called pull or load testing to 60% of its braking strength. And that's required, but that still doesn't show you that you met the manufacturer's requirements for swaging it on. Well, one way to determine that is just this. It's called a go, no-go gauge. And you use it with these swaged terminals. And what it does is it measures the amount of pressing on you've done to make sure that you have the proper diameter. Now, if you follow all the manufacturer's instructions when you're swaging on a terminal like this, the result is that you'll have swaged terminal strength that is the full rated strength of the cable itself. In other words, you lose nothing. Well, now that we've talked about cables and terminals, let's go to the next step and talk about pulleys. And here's a good example of a pulley right here. And what are they used for? Well, pulleys are used for making changes in the direction of a control cable. It comes in one way and makes a turn, goes out the other way. You'll use a pulley to do that. Now let's assume you're out in the field as a working mechanic and you are inspecting a control cable pulley like this one right here, and you check the pulley groove and you see excessive wear on both sides of the groove. Now, you look in here and you see a lot of wear inside that groove on both sides. What would that tell you? And the answer is it would tell you that you have pulley misalignment. It's not lined up properly. So excessive wear on both sides of the groove of a control cable pulley would tell you that you have pulley misalignment. Now let's talk about inspecting the controls of an aircraft. A satisfactory method of inspecting control cables for broken wires is to place a piece of cloth around the cable and run it back and forth over the length of the cable. And what happens is if you get little broken wires, it'll catch on the cloth. Now another way you could do it, not recommended by the FAA, is just run your hand back and forth and just check for blood in your hand. Now I think I'll use a cloth instead if you don't mind. All right, now when you're inspecting a control cable turnbuckle for proper installation, you determine that the safety wire ends are wrapped a minimum of 4 times around the terminal and shanks. So make sure that the safety wire is wrapped around 4 times. And that's something you need to know. Now sometimes cables should go through a little hole in the aircraft out to the control surface of the aircraft, and the hole in the aircraft is called a fairlead. The FAA wants you to know that fairlead should never deflect the alignment of a cable more than 3 degrees. So if you run the cable through a fairlead, the alignment of the cable should never be deflected more than 3 degrees. Now let's assume you're using a push-pull type control system. The threaded rod ends of a push-pull type control system should be checked for the amount of thread engagement by using the inspection hole provided. So if you have a push-pull type system rather than a cable type system, you check for the proper thread at the ends, proper thread engagement, by using the holes that aren't provided in the airplane for doing that. Now let's talk about cable tension. Sometimes big aircraft like a DC-3 or a Constellation has a tension regulator in the flight control cable system. And that's generally used in a large all-metal aircraft, and it's primarily to retain a set tension on the cable. So you might have a tension regulator in this airplane if you were flying a DC-3 or a Constellation. Now, how do you determine the acceptable cable tension range? Well, you can use a cable rigging chart. And you and I can take a look at figure 9, and you and I will see a cable rigging chart. And you have a 3/16 cable. Well, the top cable up here is a 3/16 cable. And the question says you have an outside air temperature of 80 degrees. What is the acceptable range of cable tension? Well, let's take a look at 80 degrees down here. We go down 80 degrees up until we get to 3/16. And then we read across to the left and we find out 130 pounds of cable tension. But wait a minute, up at the top it says all cable tension readings have a tolerance of plus or minus 10%. So what we're going to do is take that 130 pounds and we'll have plus or minus 10% and we'll get the range of acceptable cable tension. So let's you and I figure out that range of acceptable cable tension. 130 pounds minus 10%, well 10% of 130 pounds is 13 pounds. So the minimum would be 130 pounds minus 13 pounds for 117 pounds. The maximum would be 130 pounds plus 10%, or 130 pounds plus 13, or 143 pounds. So the acceptable range is 117 pounds to 143 pounds. Now let's take a look at a few questions the FAA asked you about helicopters. One of the questions they ask you is, let's assume you're flying in this helicopter and you manage to get the thing in straight and level horizontal flight. And I think we're eventually going to get there, maybe, maybe not. But let's assume this helicopter is flying along in straight and level horizontal flight. They're going to ask you, how does the angle of attack of the advancing blade compare to the angle of attack of the retreating blade? Well, the advancing blade is actually going faster through the air, through the relative wind, than the retreating blade, so therefore it has to have a smaller angle of attack. So the angle of attack of the advancing blade is less than the angle of attack of the retreating blade. Now, let's assume you're flying along. They want you to know, of course, there is a downwash effect as the helicopter is flying along, and there is a greater downwash effect through the aft part of the main rotor disc. And the reason for that is, of course, as the helicopter starts this front air going down and flies through that downwash, and it gets greater at the aft part because the helicopter is moving into that air. And what is that effect called? They ask you on the test, and the answer is that effect is called transverse flow lift. Now let's take a look at a few questions the FAA asked about forces on a helicopter. One of those forces they ask you about is torque effect, and they ask what direction it is in. Well, the answer is torque effect is in the opposite direction of rotor blade rotation. Whichever way the rotor blade is going, the torque effect makes the helicopter want to rotate in the opposite direction. Now, the torque force associated with a single rotor helicopter is compensated by the tail rotor. And you use a tail rotor with a variable pitch mechanism, and it's actuated by pilot controls, which is pedals. And I want to call them rudder pedals, but they're not. They're called pedals. Now, the tail rotor blades compensate for that torque, and they're going to ask you what happens if you have a decrease in the pitch angle of tail rotor blades. And the answer is you have just exactly that. The tail tends to pivot in the direction of torque rotation around the main rotor axis. Now, one of the things you'll be interested in as a mechanic out there in the field working on helicopters is rotor blade tracking. And what you want to know, does the path of one blade follow the path of the other blade? And if the path of these two blades are the same, they are said to be in tracking. So one of the things you want to check is main rotor blade tracking. And the purpose of checking that is to determine the flight path of the blades during rotation. Now, when you pull up on the collective and get this aircraft ready for flight, the blades will cone up. And main rotor blades that do not comb by the same amount are said to be out of track. Now let's take a look at what you need to know on the FAA written exam about the controls of a helicopter. They're going to ask you, how do you control the vertical flight of a helicopter? Well, you do that by increasing or decreasing the collective pitch, and therefore changing the pitch angle of the main rotor blades. They're also going to ask you, how do you control the movement about the longitudinal axis? Well, movement about the longitudinal axis is roll, and you do that with the cyclic control or the cyclic pitch control. When you move the cyclic pitch control to the left, the helicopter wants to roll to the left. Now, they also ask you, how do you control movement about the lateral axis? Well, that is pitch, and that also is controlled with the cyclic pitch control. So you do that by moving the cyclic fore and aft, and that changes the pitch of the helicopter. Now, they say, let's assume that you're in forward flight cruise configuration. How do you change direction of this helicopter? Well, the way you do that is by tilting the main rotor disc in the desired direction. The cyclic control really does it, but it tilts the main rotor disc in the desired direction. Now, let's assume you're in a hovering helicopter and it's equipped with a tail rotor, as this one is. How do you maintain directional control? And the answer is by varying the pitch of the tail rotor blades. You, of course, do that with pedals. Now, let's take a look at a couple helicopter components they want you as a mechanic to know about. As you know, the way a helicopter works is the engine is driving this main rotor up here. So it is a very good idea to have the engine connected to the main rotor. But if that engine should quit or slow down so that it's no longer driving the main rotor, it's not such a good idea to have the main rotor connected to the engine, because the engine is now slowing down the main rotor. In the event of an engine failure, it's very important to maintain rotor RPM, so you don't want the engine slowing it down, so therefore there is a solution. And that solution is called the freewheeling unit or freewheeling clutch, and it automatically disengages the rotor in case of engine failure. Now, they're going to ask you on the test, why do you have a freewheeling unit? And one of the things they'll say is to reduce or relieve the starter load. No, that's not correct. You have another clutch for starting the engine. The purpose of it is to allow you to be able to fly the airplane or aircraft in the event of an engine failure and to keep the rotor RPM up. Now, they'll also say so you can practice auto rotations. Well, it's true, you can practice auto rotations, but that's not the purpose of it. The purpose of it is to disengage the rotor in the event of, and terrible thought, an engine failure. Well, one of the neat things you can do with a helicopter is pick up external loads. Now, would you say a truck qualifies as an external load? You bet it does. And if you want to pick up something like this, you'd like to locate this cargo release and the hook at the best location. Now, where is the ideal location of the cargo release? Well, how about where the line of action passes through the center of gravity at all times? That way you won't be making wild changes in the center of gravity of that helicopter when you pick something up or release it. Now, believe it or not, you and I have covered everything they're going to ask on a test about assembly and rigging. And when you realize the vehicles you're working on are going to do things like this, then you realize how important assembly and rigging are.